that, we get a fourth degree tensor, a quartic differential, and that's again holomorphic. So because this one's holomorphic, not hard to see, the quartic one is also holomorphic, and it's also real along the boundary. In fact, along the boundary, it's actually a positive, a non-negative real function, because it's just the real part of phi dotted with its x. It's the square length of phi. Okay, and so the fact that we're on the disk and the fact that phi is real along the boundary implies that it's identical. Well, it implies that phi is identically zero. Phi dot phi is identically zero to disk, and then because on the boundary it's just the square length of the real part, that implies that phi itself is identically zero along the boundary. The phi is a holomorphic thing, and it's zero along the boundary, and so you can then argue that it's identically zero in D. Okay, and so that implies the second fundamental form is zero at sigma flat disk. So this actually came as quite a surprise to us, just following the analog with the sphere. So let me just say that the result is also true for surfaces of constant mean curvature. Actually, Richard originally proved it here for constant mean curvature surfaces, and in fact, this generalizes that thing too. So you have to assume parallel mean curvature. So if you have in Bn a proper disk which meets the boundary orthogonally with parallel mean curvature, then it's either a flat disk, as in the previous case, or it's a spherical cap. So it lies in a copy of R3, or it's just a spherical cap that meets the boundary orthogonally. And it's also true for disks with parallel mean curvature in any ball in a simply connected spaceplane. Simply connected space of constant curvature. It meets the boundary orthogonally, and then it's an umbilic surface. It lies in a three-dimensional subspace form. So you might ask, well, how does this interact with the fact that there are lots of minimal S2s in Sn? Well, the consequence is that if we take a minimal S2 in Sn, if it's invariant by reflection through a hyperplane, that is, if there's a hyperplane of Sn and the surface is invariant by reflection, so that would make it a free boundary solution in the hemisphere defined by one side of that hyperplane. Then it's in fact an equatorial S2. And so that's the connection with minimal S2s and Sn. Okay, so right. And so in my Wednesday talk, I'll say a lot more about the connections between these free boundary minimal surfaces and the iron. Okay, so I think I'm out of time for today, so I'll stop here.
Are there any questions?
Criticisms?
Suggestions? Okay, but if not, then let's take this week. Before we leave, I want to make an announcement so that we'll have a group photo here taken. So please don't leave.